Okay, so yeah, let's get started. So last time we started to discuss some ideas about the Monte Carlo method. And the basic idea for the Monte Carlo method is basically it's all about basically how we're gonna do some kind of the get some kind of numerical approximation for the integral of the computation. So in case when we cannot basically find some kind of the analytical solution for the integral, we are just taking some kind of the numerical approach to get some kind of the approximate, some kind of estimate for the integral. And there are actually multiple the other ways around basically being some kind of the get some kind of estimate for the integral. But the power of the Monte Carlo method is in basically simplicity. So it's kind of the stochastic approach in terms of that. Once you have some kind of the some indeterminate the samples that are basically samples from some kind of the certain the probability density function, based on that we can define the Monte Carlo estimator shown in this slide. Let me yeah. It's shown here, for any kind of given the probability, the density function, we can basically have some kind of lots of the samples, and we can use those samples to basically estimate any kind of integral. So it doesn't need to be 1D integral, but for in any kind of the multi-dimensional space, we can use the same approach by just having this kind of some of the samples and the estimate. And one of the good thing of the Monte Carlo estimator was that it was basically the unbiased the estimator, which means that we can expect that the output will be the same, will be equal to the integral. So which means that when you calculate the expected value of the estimator, we can prove that the expected value is the same with the integral. So that's the case that we are having the unbiased the estimator. And we could also basically consider some kind of the efficiency of this kind of estimator. So we need basically care about like both the variance of the estimator and also the computation time of the estimator. Based on that, we could also define the efficiency of the estimator. So those are basically things in terms of like defining some kind of estimator. And while we also discuss some kind of unbiased estimator, there can be some kind of other types of some biased estimator. Which is the case that the expected value does not exactly match given the integral of the function that we are calculating. But actually, the kind of good thing was that, I mean, the key thing was that even in this kind of the case that we are having the biased estimator, the thing we need to do, we need to basically check out is that this still might be the case that we can basically see some kind of the convergence to some kind of the true value. So that was kind of the example that we are seeing in the last lecture. So for the Bessel-stick correction case, even with some kind of the biased the estimator of the variance, we could see that actually the estimator can converge to some kind of a true value when the number of the sample is going to the infinity. But it's just like the bias, which means that when we do not have the kind of infinite number of the samples, the output may not exactly matches the number that we want to get. But in some of the cases, such kind of the biased estimator still can be useful, especially when the convergence the rate is much faster than the unbiased the estimator. So which means that in practice, in many of the cases, obviously, if we can have some kind of the unbiased estimator, it's always good to have some kind of the unbiased estimator. But in some very special cases, when we can basically define some kind of the biased estimator, which converges much faster than the unbiased estimator, then we can consider using this kind of the biased estimator. So this was kind of the one key thing. And it's kind of the way to basically improving some kind of the efficiency in terms like calculating this kind of the estimator. One of the idea that we also discussed last time was basically the stratified desampling. So this was the idea that we are partitioning the domain of the integral into some kind of some multiple regions, and then allocating the samples into each of the partition based on kind of the probability density function that we are also defining for each of the partition. So one of the key things that we also could see last time was that basically this kind of a stratified sampling is not increasing the variance at all. So which means that it's always good to basically try to do some kind of a stratified sampling, basically dividing some region into some kind of some multiple pieces, and basically doing some allocating the samples into each of the region. So one of the simplest idea in terms of like the allocating the samples into the region was based on using the kind of the area of each of the area or the volume of each of the region, and then doing some kind of uniform sampling for each of the regions. So this was kind of the very simple but effective way to basically decrease the variance and also getting some kind of the more accurate estimate of the kind of the integral. So this was kind of the basic idea that we discussed last time. And today we're also going to discuss some more ideas in terms of like how we can also improve the efficiency of the computation, the estimate. So really the most important part in the Monte Carlo, the estimator is basically utilizing some kind of importance sampling. So here the key idea is that when you define the Monte Carlo estimator like this, what actually we can see is that if we, so it's all basically a matter of like how we define the probability, the density function here. Yeah, here. So the good thing of the Monte Carlo estimator is that we can choose any arbitrary the probability density function for the sampling. So the simplest idea was basically just using the simply the uniformity distribution. But depending on basically the probability density function that we are picking here, actually we can see some kind of different kind of convergence rate for the estimator. So actually one kind of the example is that if we pick the PDF function here as kind of the function which is basically proportional to the function value of the f here, then we can actually see some kind of the very fast convergence rate. So if we think about like this kind of very special case, when the PDF is defined as kind of the same as the function divided by basically the integral of this function. So this can be kind of the one way that we can make some kind of the PDF that basically satisfies some kind of conditions for the PDF, right? The integral of this, the PDF, the function over the domain should be one, right? So this can be the easiest way that we can make some kind of the PDF from the function df. And in this case, what we can see is that if we plug in into this the Monte Carlo estimator, that we can see that for any kind of the random variable, this kind of the f divided by the p, this term becomes the constant, right? As kind of this integral of the value. Then this becomes the case that we are kind of like achieving the zero variance. So we can always get some kind of the perfect outputs. But obviously it doesn't make sense because our goal here is to basically estimate this interval. So it's kind of like chicken and egg problem. So if we can obviously get some kind of the integral of this function, then we can also get the like zero variance the estimator. And actually we don't need the estimator because we already know this value, right? So this is really kind of the chicken and the egg the problem. So here the question is that in the case that when we cannot basically have the full access of the information about the function f, and also when we cannot directly calculate the integral of the function f, how we can basically define some kind of the probability density function, which is kind of like having the similar shape with the function f here, in terms of like basically decreasing the variance of the estimator. So that's kind of the key idea of the importance sampling. So let's do some kind of some simple exercise with this kind of function. So let's say like we are having this kind of the shape. Maybe yeah, here basically let's assume that even we don't know the analytic form of this function. We just have some kind of the sense that the shape of the function will look like this. So when you have this kind of some very weak information for the function, that the function will basically look like this. What we kind of the way that we can define some kind of the simple probability density function that basically had the similar shape with this in terms of like decreasing the variance. Do you have any kind of a suggestion in terms of like doing some important sampling for the PDF here? Yeah, so there are many kind of the answers here. I mean, yeah, obviously there can be the multiple the options. Like one simple kind of the way would be basically having this kind of the had like the shape of the function. So we are having this kind of the probability the density function in terms of that we are having the very low the probability for the region here and high probability for the region that we can see some kind of a concentration of the function. So actually, depending on the probability density function that we are picking here, we're gonna get some kind of have the different variance. So I also strongly recommend you to basically try to calculate the variance for each of the different choices of the probability density function. So without any kind of some special the PDF, but when you just use the simple the uniform distribution, then we can get actually we can see that the variance becomes the 0.00365. So actually, this number, the variance here is the number that I also calculated using the ChatGPT. So actually, I just copied this example from the physically based rendering the book, and I just verified that the number in the book is the same that the ChatGPT can also calculate the variance with its function. But I also recommend you to basically try yourself, basically calculating the variance using some kind of a function that you get. And especially these are the variance that when we just have the uniform distribution, and if we choose different the distribution here, then obviously we're gonna get some kind of the different the variance. So especially in this case, when we pick this kind of the PDF function here, then we can see that the variance basically decreases into the 6.7 times, much is smaller, which means that we're gonna see some much faster the convergence rate with the number of samples. So yeah, I recommend you to basically try to calculate the variance using the PDF that you're answering here and see how much you can decrease the variance with the choice of the PDF. But here also the question is that when you basically pick any kind of the PDF here, which means that when you have the PDF this function, we also should be able to basically sample based on the probability density function, right? So for some simple cases or some special cases, like we are having the uniform distribution or some Gaussian distribution, for those cases, we know basically how we can simply sample the points based on the PDF. But also the question here might be is that when you have some kind of the arbitrary the PDF function, then how we can also generate the samples based on this PDF. So this is also what we are going to briefly see here. So let's first see some kind of the simplest the case here. So let's assume that we are having the discrete the probability distribution like this, that we are basically having some kind of the n number of the discrete values xi here with some kind of the probability for each of the value. And since we are basically having the PDF, then the probability basically should satisfy these kind of the two conditions, right? So the sum of the probability should be basically 1. So when you have this kind of like the n the pairs of the numbers and also the probability, how can you basically sample one of the values based on the probability? What should be kind of the basic idea for this? Any ideas? Like when you have the n number of the values and the corresponding the probability the value, then what's the way that we can sample one of the values according to the probability the density? Yeah, this is something that you should have learned in the introduction to statistics course. Now, one simple way that we can think about this is that basically we are thinking about some kind of the cumulative the distribution the function. So we are basically accumulating the probability density for in the order that we are having the all the values. Then what we can see is that each of the value in the discrete set, we can assume that basically each of the value in the discrete set is basically partitioning the range from the 0 to 1, right? So if we see some kind of the cumulative the probability density for each of the value, this might be the cases that we are basically seeing some kind of the split of the range from the 0 to 1 with the cumulative the kind of the probability density for each of the values. So what we can see is that actually we can sample based on the cumulative the probability the density. So which means that all the cumulative the probability density should basically satisfy this kind of rules, right? All the numbers should be in the range from the 0 to 1, and at the end we should the cumulative the density should be basically the 1. So what we can do is that we are now sampling based on this cumulative the probability density, which means that once we basically have some kind of the uniform sample in the range from the 0 to 1 here, based on the sample, now we are basically choosing the discrete value, which is corresponding to that specific the range of the cumulative the probability density. So this is basically the very simple the idea that we are doing some kind of the inverse transform desampling, right? So this is basically nothing but when you have some any kind of the PDF function, we will compute the CDF, the cumulative the density function, and then we are sampling based on the cumulative the probability density, which means that we are having the uniform the random variable in the range from the 0 to 1, picking one of the cumulative the probability density, and then finding the discrete value which is corresponding to this kind of the cumulative the probability density. So this can be like the very simple the idea that we can apply into the any type of the probability density. And we can also apply the same idea not only for the discrete the probability distribution, but also for the continuous the probability distribution. We can do the same thing, right? So when you have the PDF here, we can also calculate the cumulative the probability density function by taking the interval like this. And then we can also apply the same idea. The sampling with the PDF here becomes the same, that we are first sampling the uniform, the random variable in the range from the 0 to 1, and we are taking the inverse function of the CDF in terms of like finding corresponding the value with this kind of the cumulative the probability the density. So this is the very simple the idea, right? But here also one thing is that this basically means that we should be able to be basically compute the not only the CDF but also its inverse of the CDF. So this means that basically when you define some kind of the PDF, we should be able to consider like how we also calculate the inverse of the CDF as well, right? So when we can basically define the inverse of the CDF, we can easily sample based on the probability density function, and then we can apply the idea of the importance the sampling. Some simple idea. So let's also do some kind of a simple, some kind of the exercise. So let's first try to see, like, let's say like we are having the function that is just like nothing but like x squared in the range from the 0 to 1. Then if we want to find the probability density function, which is basically proportional to the given the function, what would be such kind of function, the px here? So maybe we can take some time in terms of like we calculate such kind of the PDF the function and also the CDF function and also its inverse as well. So if you found the PDF PX here, let's also calculate the CDF PX here and also the inverse of the PDF CDF as well. Yeah, so this is like just the simple the case that we are having like such kind of the PX. So the here the ratio C can be easily calculated by just making the integral of like this function to be 1, right? Then we can easily see that like the C becomes like 3/8. Then we have the obtaining the PX like this. And this is obviously a function that we can easily calculate the CDF as well. So the CDF will becomes like 1/8 of the XD cubic. And the inverse of the CDF will be defined like this. So this is kind of like one simple example that when you have any kind of the analytic form of the PDF, like especially into the polynomial function, then we can easily calculate inverse of the CDF, and then we can do the sampling based on the PDF using this the technique of the inverse transform desampling. Yeah. So yeah, this is kind of a simple example. So, I mean, important sampling is one of the actually also important the technique in the Monte Carlo estimates. So we're gonna also get into some kind of the example like how we're gonna utilize this technique for the ray tracing the framework. And you actually see that like all the things that we are doing in the ray tracing the system is all about basically doing some kind of the Monte Carlo like the integral the computation with some techniques of the sampling. So those might be kind of the main idea that we're gonna see in the ray tracing the system. So yeah, so in terms of the sampling, actually, even not for the the important sampling, actually there are some many kind of some specialty cases that we need to sample not only some kind of some specific sample the area which is defined as kind of some bounding boxes, but we can also consider sampling from some kind of some specialty regions or some kind of even some kind of non-uniform or some non-manifold some kind of spaces. So as a kind of one of the examples, what we are also going to see is that like if we also sample like the points, especially uniformly sampling the points in a kind of unity circle, then what would be kind of the best way to do this, right? So let's get into like this specific example. So if we want to like uniformly sample in a kind of the unit circle, one kind of simple the idea might be utilizing the polar coordinates, right? So we are basically representing any kind of the point with the r and the theta. And then one simple way that we can do some kind of sampling in the unit circle might be is that we are uniformly sampling some kind of the angle the theta in the range from the 0 to the 2 pi, and also sampling the radius from the range from the 0 to 1. Then we're gonna get this kind of the some XOYD point, right? Does this make sense? What the kind of problem that we are having this kind of the sampling? So actually, if we sample like this, then actually we are not getting some kind of the uniform the samples. What the reason for that? Okay. So if I give some more hints, like why we are not getting the uniform the samples, then actually the output of this sampling becomes like this. So you can see that we are having some more like some sort of the concentration at the center of the circle. While the uniform sample that we want to see is basically this kind of the output. We are having some kind of the more like distributed the points in this case, right? And here the question is that why we are having some kind of the concentration at the center, right? So here the reason that like why we are basically getting some kind of the more the concentration at the center would be because of the fact that we are uniformly sampling the radius, right? So which means that when you think about every some kind of the circle like this, some kind of the ring. Let's say like we are having some kind of the ring here with some kind of the infinitesimal the width of this kind of ring, right? So when you think about like this kind of like infinitesimal the width of the ring, having some kind of the also the some kind of area for each of the circle. There is basically all these kind of circle at the same the probability to be picked because we are having the uniform the samples of the radius, right? So basically, those kind of the circles might have the same the probability to be picked, but we can say that like the the area of each of the ring is basically different because the area will be basically defined as kind of the 2 pi r times of the delta r, right? So as you can see, as we basically go further from the center to the outside of the circle, we're gonna basically see that the area of this kind of the ring is being increased while we're having the same the probability to pick each of the circle, right? So that's why we are basically having some kind of concentration at the center. Since as we get closer to the center, the area of the region to become smaller, while we are having the same the probability to pick that region, right? So here the question is that how we basically change the sampling the probability the density function in a way that we can get some this kind of the uniform samples. So what we can actually see here is that let's see this kind of the case. So let's say like we are computing some kind of the infinitesimal the area of any kind of the point in the unit circle using the polar coordinates. Then we can see that for each of the point here, the area of this kind of region becomes like dr times r d theta, right? So from the definition of the angle here, so this length will be the subtended from the small angle the d theta here, right? We can see that this small region is basically has the area of the r, dr actually times r d theta. So that becomes this, right? So the infinitesimal area for each of the point becomes this. And then what we want to do is that we want to define the probability density function in terms of that becomes basically proportional to this kind of infinitesimal area, which means that we want to define the probability density function p here in terms of that this becomes the function which is basically proportional to this area. So this basically means that we want to define the probability the PDF here, which becomes like has the some certain the constant ratio with the radius r here. Is this clear? Then here the question is basically how we're gonna define this kind of the PDF. And what we can see is that now we are defining, sampling the theta with some kind of the uniform distribution. And then what we are seeing is that we are now sampling this R and the theta independently. So we can see that now this PDF can be decomposed into this form. And also here what you can see is that this PDF is decomposed like this, and we know this probably the density function, right? Which is the uniform distribution. And here the question is that when you know this kind of the fact, and when you want to make this kind of this PDF to be have some proportional to the radius R here, then how should we define this kind of the PDF for the radius the R, and how can we also sample based on the PDF? So let's think about this. Yeah, so as you can see, like this might be kind of simple in terms of that we are now seeing that it's like the PDF for the setup becomes like nothing but like 1 over the 2 pi, right? And we want to make probably the density function for the R to have this form. So it's a matter of basically finding this kind of the constant term C here, right? So by taking the integral of this kind of PDF, we can see that the C should be basically the 1 of the pi. And based on that, we can see that the PDF now becomes 2 times R, right? So which means that if we want to have some kind of the uniform samples so inside the unity circle, we should not have some kind of the uniform distribution for the radius dr. But actually, this PDF for the r should be some kind of the linear function with the radius r here. And based on that, what we can also see is that the CDF, the cumulative distribution function for the r becomes the r squared. Then we know we have all the information about the PDF and the CDF, and we can also have some kind of calculate the inverse of the CDF here as well, right? So based on that, if we really want to have some kind of uniform samples inside the unit circle, then what we can do is that for the radius, this becomes some kind of the inverse of the CDF. For the angle the theta, we can also have the inverse of the CDF like this. Then what we need to do is that we are basically sampling the two uniformly random variables in the range from the 0 to 1. And then we can basically take the square root of the first one and also 2 pi times the second one as kind of the r and the theta like this. So this can be some kind of the simple way that we can also do some kind of the uniform sampling in the unit circle. Does it make sense? Obviously, we can even try something like even simpler the way. The other kind of simpler way that we can do this kind of thing might be is that we are basically doing some kind of the rejection sampling. especially when we do have some kind of like not having this kind of some simple region, but when we have some kind of complicated some kind of the shape, where basically we need to do some kind of sampling, we can consider having these kind of the bounded boxes, and basically just sampling inside the bounded box and rejecting some samples that are outside of the region. Obviously, the problem here might be is that we are losing some kind of the samples for the points that are not inside the region. So there you can also think about some kind of the success rate, the efficiency of the samples, like how many of the samples will be really used in the final calculation. So this can be another simple approach. So let's also do some kind of the extension from the circle in the 2D space into the sphere. So that's actually kind of the main purpose of like doing all those kind of things. So if we can basically sample inside the unity circle, what about like the case that we are sampling the points on the unit sphere? So this is the case that like we now want to sample the points over the surface of the unity sphere. So in these cases, we can also represent each of the point with the spherical coordinates, right? Having the theta here and also the pi. So now the theta becomes the angle between the axis to the North Pole to each of the direction, and also the pi becomes some kind of the axis of the angles of the azimuth, right? So actually, the meaning of like this is that if we can uniformly sample points over the surface of the unit sphere, this is basically means that we can do some kind of uniform sampling of the direction, right, in the 3D space. So without the scaling, if we want to do some kind of the uniform sampling of the direction over the 3D space, we can actually consider sampling the points over some kind of the unit sphere. So those are also the cases that each of the points can be represented as some kind of the having some kind of the infinitesimal area, which is basically calculated like this, right? And since we are also having the unity sphere, the R square becomes the 1, right? We are having this kind of the infinitesimal the area. And we want that probably the density function for the p theta pi to be basically proportional to this kind of the infinitesimal the area, right? For these cases, how should we define probably the density function for the p theta and also the p pi? Then let's also see how we can also compute the CDF and how we can also do some kind of the sampling based on this kind of probably the density function. So let's try this out. Yeah, so we are sampling on the surface of the sphere. We can also think about the case that we are sampling inside the sphere. So that would be kind of another the exercise. But let's just think about the case that we're sampling on the surface of the sphere. Yeah, we can also just sample these 3D points and normalize them. But what would be the problem of that? If we simply like sample 3D points and normalize them, the problem would be is that they do not be having the uniform samples, right? So in the case of like, so we can also think of like sampling the points on the circle, right? Not inside the circle. For those kind of cases, we can also consider basically sampling the points inside any kind of 2D points and normalizing the points, right? Actually, we can see that like this kind of the simple approach may not be really having some uniform samples. So let's think about the case that we are only sampling the theta and the phi. And this is the case that we are having the unit sphere, which means that R is fixed to be 1, right? So this is kind of like similar to the case that no, in the previous case, we had the P R d theta, which should be proportional to R. In the 2D, the circle case. Now, in this kind of like 3D case, we see that the P theta pi, this is not the same theta, but the different theta, T should be basically proportional to the sine theta, right? So did you even get results like this? Is it the same as you calculated? So it's exactly the same approach that we are basically now finding some PDF for the theta and the pi in terms of that becomes the function which is basically proportional to the sine theta. And we also want to sample the theta and the pi independently, or basically fixing the PDF for the pi to be kind of uniform the distribution. And we can see that now the PDF for the theta should be have this form, right? And if we calculate the C here, then we can see that actually this P theta, the PDF for the theta should be basically the half the sine theta, right? Clear is the results that you got. And then if we take integral to compute the CDF of the theta, then we can now have this form of this kind of the CDF the function. So if this is not the same with your calculation, maybe you can check this out after the lecture. So I will also post all these slides in our the course web page. So these are some kind of the calculation in terms of how we're gonna do some kind of the uniform sampling only the unit is pure. Then what we can see is that according to the CDF in the previous slide, now we can basically calculate sample the theta and the pi with the uniformly random variables. And if we think about the spherical the coordinates, the x and the y and the z coordinates becomes like this. So while we are having some sort of the some complex terms here, what we can see is that we can first calculate the z with one of the random the variables, and then by just taking z here, we can calculate the x and the y like this. So this is kind of like one simple way that we can do some kind of the uniform sampling on this sphere. And this like the uniform sampling on a unit sphere is actually one of the very essential part in the ray tracing. And can you guess why? So yeah, we're gonna get into that. So we're gonna start to go back to this kind of the reflection the equation. But what we are basically doing in our the rendering equation was basically calculating the outgoing the radius by basically collecting all the information from the incoming the radius. Which means that for all the kind of the direction, which is represented with the solid angle, we should be basically able to do some kind of a sampling. So which is really sampling of the direction in the 3D space. And then as I said, like sampling direction in this 3D space actually becomes the same as kind of like sampling points over the unit sphere or some kind of the unit hemisphere. So for those kind of like sampling of the solid angles, you can actually use this kind of the technique. Basically, this formulation. So this is basically what we are going to see. And as you can see, like all those things, like you'll be also able to see that the other some types of the uniform sampling also becomes like easier. So maybe you can also think about like how we can do some kind of the uniform the sampling on some kind of the unit the hemisphere. So that can be also another thing. And also we can consider uniformly sampling the points not on the surface of the surface of the sphere, sorry, but also basically inside the unit sphere. So those cases, what should be kind of the R and the theta and the pi that we are taking. So those might be another kind of things. And also if we are basically sampling points inside the unit sphere, we can also consider like having some kind of the rejection desampling. But if we take some kind of the rejection desampling, then what would be kind of the success rate? How much this kind of resampling would be kind of the efficient, depending on the bounding box that we are having. So those might be some kind of the questions that we can consider doing some kind of the sampling. Any question on this? It's clear. So these are basically some kind of the basic things in terms of like, doing some kind of the calculating the Monte Carlo the integral. And we are going to see basically how we can apply this kind of the idea in our the, calculation of the rendering. So let's first see some kind of the cases that we are taking some kind of the calculating some direct the illumination. So if we go back to our the rendering the equation, so the rendering equation was defined like this. So as I said in the previous lecture, the rendering is all about basically calculating the radius for each of the direction. And what we can also see is that if we have some kind of the reflection of the surface, the reflection is basically the case that we are collecting the information of the incoming radiance from the all the direction, and then taking the integral with some kind of the ratio of some kind of reflection for each of the incoming and the outgoing direction. And then adding some kind of some factor of the emission in the case that when the surface is also kind of emitting some kind of a light source, and then we are calculating the radiance for each of the outgoing direction. So this was kind of the basic the equation of the rendering. And this function defines some kind of the ratio of some kind of the light transport from for each of the incoming and the outgoing directions was the function which was called the BRDF, right? And we have seen that this like BRDF is basically characterizing some kind of the material properties of each of the surface. So as you can see here, the key part is that we should be able to basically sample the solid angles over the hemisphere, right? So when you have this kind of the surface, that we are assuming that locally, this is kind of the point that we are having some kind of the flat, the plane. We are basically sampling the direction into the any kind of the points over the hemisphere. So which is really the case that we are sampling the points over the hemisphere. And then basically, calculating all these kind of terms, and this integral now can be estimated using the Monte Carlo method. So this is kind of the basic idea. Obviously, with this like random equation, there are some kind of specialty cases that we may not need to use some kind of the Monte Carlo method. Like one specialty case is that when you have some kind of the specular BRDF. So as I also mentioned last time, we can also have some kind of some sort of the mirror-like the shape, where basically we see that the BRDF the function is defined like this. So here basically we get some kind of the value of the one for the BRDF when the incoming and the outgoing the direction of the vectors basically satisfies the angle of the reflection, right? So when you see that like this angle and this angle are basically the same with respect to the surface normal direction here. So basically when you specify the outgoing direction, where basically we want to calculate the outgoing the radiance, and for each of the incoming the direction, if we see that these two directions basically satisfy the condition of the angle of the reflection, then we are basically making the BRDF to be 1. Otherwise, we are making this to be 0, right? So this is the case that we are having this kind of Dirac delta function, right? So basically here, the delta here means basically the Dirac delta function that when this BRDF becomes 1, when these two are basically the same. Otherwise, this BRDF becomes the 0, right? So this is the special case that we are having the perfect the specular refraction. And this specifically like this specular reflection is characterized not with the incoming the differential the irradiance, but with the differential with the incoming irradiance and the outgoing irradiance. So we are having this kind of the BRDF term, which means that the rendering equation turns out that we are having this kind of this rendering the equation where we don't need to take any kind of integral, right? So this is kind of a special case that we can directly calculate this rendering the equation without calculating the integral. And also the other special case might be that we are also having some kind of the direction of the light. So for example, when we assume that the light source is very far from the point that we are calculating the reflection, for example, like when we have the sunlight. So those might be the cases that we can basically have some kind of the BRDF function like this. It's not the BRDF function, sorry. The kind of we can see that the incoming the radiance is defined like this. So which is the case that we are having the incoming radiance when the incoming direction is the same with the light direction. Otherwise, we are basically having the 0 the incoming the radiance. For those kind of the cases, we can also see that we can calculate the outgoing direction like this. So here we are basically plugging this kind of the visibility term. So unless we are having some kind of the occluders here, when we calculate some kind of reflection, then we can directly calculate all this kind of term. But if we have some kind of the occluder, basically occluding this kind of light from the light source, then we are basically having the 0 visibility here, that we are making the outgoing the radiance to be 0. So those are some kind of the specialty cases that we can calculate the outgoing irradiance without calculating the interval. But for some kind of the general cases, as I also mentioned, we can consider using the kind of the Monte Carlo estimate here, right? So when you have this kind of the reflection the equation, what we can do is that we are doing some kind of like sampling some kind of the solid angle over the hemisphere. So we can consider having some kind of the uniform sample. So the good thing of like having the uniform the sample is that we know that the probability basically becomes the constant number. Then the Monte Carlo estimation becomes like much easier, right? So we need to have like this term, right? Pxi, taking the sum of like those things, right? So if we know that this, the probability is kind of the constant value, then the computation becomes like much easier. So that can be kind of the way that we are not utilizing the importance sampling, but making the computation becomes like easier, right? So for those kind of cases, we can do some kind of the uniform sampling over the hemisphere, having some kind of the uniform distribution of the all the solid angles, and doing some kind of the calculation here, and having this kind of the Monte Carlo the estimate, right? So from the previous slide, then we see how we uniform sample the points over this sphere. Actually, you can also calculate this, right? So when we represent each of the solid angle with some kind of the theta and the pi with the spherical the coordinates, instead of like directly sampling the uniform the solid the angle, we can sample the theta and the pi, and then we can calculate the probability the density here. Okay. So for those cases, based on this, we can do have some kind of the Monte Carlo estimate of this kind of reflection. So this is really kind of the very basic idea of like how we do some kind of the ray tracing and how we calculate the rendering the equation, right? But actually, for many of the cases, this kind of the simple the Monte Carlo estimate has some kind of issue. What would be the problem that we are having this kind of the Monte Carlo estimate? I also give some kind of hint for this, like when you do some kind of some naive the sampling of the solid angle, that we are getting this kind of output, while the right one is basically something that we want to get, right? So this is kind of like very simple the example that we are having the light source here, and then some kind of the occluder in the middle of the space, right? For those cases, if we uniformly sample the solid angle over the hemisphere, then we get this. Right? Well, actually, the answer is kind of simple. Like for all this kind of like the calculation of the illumination, we want to see the effect of the light source, right? How much of the some kind of the light which is coming from the light source is basically affecting some kind of the illumination for each of the points. So here, kind of the key thing is that if we just like uniformly sample like all the direction over the hemisphere, there might be actually very few the samples of the points, actually the directions, which are really hitting the light source and contributing the illumination. But many of the kind of the directions will not really hit the light source, which means that these are basically some kind of the samples that are not really contributing the final calculation. So kind of the practical way that we can do some efficient sampling or some important sampling is that we are not sampling the directions, but actually we are sampling the points over the light source. So let's especially think about this kind of a case that we are having some kind of the area light source here. So now the light source is defined some kind of some plane or some kind of some region, some 2D the plane in this rated space. For those kind of cases, like instead of like sampling some directions over the hemisphere, what we can do is that now we are sampling over some kind of the points over the area the light source. So for those cases, now we can replace the differential of the solid angle like this. Because from the definitions of the solid angle, what we could see is that the area, which is basically the perpendicular to the direction of this kind of direction from the point to the light source, this basically area, the area which is perpendicular to this direction, becomes the area which is basically subtended by the solid angle, right? So which means that when this area is basically dA times like cosine d theta. So here d theta is basically theta here. The angle between the direction from the point to the light source here with the surface normal of the area of the light source. We're given this angle, this the projected area, which is also known to the view direction, becomes like dA times like cosine d theta. And from the definition of the solid angle, we can see that this becomes the same with the r squared times like the differential of the solid angle, right? From this, what we can see is that now we can replace the differential of the solid angle into this term, right? So this can be the same kind of the formulation that we are simply replacing the differential of the solid angle with the differential of the area over the area of the light source. And then we can now also have some kind of the constant the light source. So I mean, we are assuming that the incoming the radiance coming from any point of the area of the light source is basically the same. So we are having the constant the incoming radiance here. And then we can also easily plug in the visibility term where we're having some kind of occluder or not. So this is basically some kind of additional term to calculate the visibility. So yeah, so this is the similar with the previous case, but we are now sampling not some kind of the direction uniformly, but actually sampling the points over the surface of the light source uniformly by the area, and then converting the solid angle into the differential of the area. And then now you can also compute the Monte Carlo estimate into this form, right? So this is nothing but we are basically replacing the sampling of the direction into the sampling of the points over the light source. And what will be kind of this term? So this is the probability, right? This term should be basically nothing but basically one of the area, right? Because we are uniformly sampling the points over the light source. So this can be sort of like considered as kind of like doing some sort of the important sampling, right? So we are basically changing the kind of the domain where we are basically sampling some points in a way that we can have some kind of the different estimator for the same reflection equation. So this is the case, and now calculate having some kind of the estimator by sampling the solid angle. And this is the case that we are having the same estimator for the same equation, but not by sampling the solid angle, but sampling the points over the area of the light source. So which can be kind of the more effective way, because we can say that like all the points that we are sampling over the light source will contribute to the basically the computation of the illumination. Make sense? Yeah, so those are some of the cases that we are now sampling the points over the light source. Then we can get some kind of the much better the quality of the outputs with the same number of the samples. Any questions on this? Yeah, so these are like some kind of cases that we are calculating some kind of like single step the reflection. And here one of the questions might be is that then how can it really get some kind of the final the rendered image, right? For the final the rendered image, what we are going to assume is that we are going to assume that in the film the plane, if we do not somehow ignore some kind of effect of the lens, the camera of the lens, then we can basically assume that what we are recording with the film is basically the information of the irradiance. So for each of the pixel in the film plane, now we can calculate the irradiance, basically calculating this. And this can also have this kind of form in terms of also sampling the points over the surface. Then using the same Monte Carlo method, we can also finally like calculate all the irradiance for each of the pixel, and that becomes the information that we are basically recording into our basically the rendered image. And as we also discussed in the last lecture, as we have some more samples of this kind of the Monte Carlo estimates, we can see that the variance will basically decrease linearly with the number of the samples. So these are also some of the examples, like when you have the only one single D ray for each of the pixel, and also when you have the 16 rays for each of the pixel, right? For those, with the two cases, we can see that we are getting so much kind of the smoother, and so the rendered image, which is really kind of like getting closer to the ground truth kind of the outputs. And these are also some of the examples, like when we also increase the number of the samples, how much we can basically decrease the error of the rendering, right? So these are the number of the rays that we are getting. And we can also see some video for this. So as we have some more number of the samples, we can get some kind of the rendered image, which is like getting closer to some kind of the real of the outputs. Right? Let me play this again. So these are basically, I mean, as we basically increase the number of samples, we can get some kind of some more like finer the outputs with some better quality. Yeah. Also, important sampling is also important for the rendering as well. So depending on some kind of the situation, like, so this is actually the cases that we are having some multiple the light sources. Then here the question is that how should we basically sample the light sources depending on like which information. So if we just like uniformly sample all the light sources, then we can get this kind of the output. But if we use some kind of trick of the input sampling in terms of like sampling the light source, proportional to the power of the lights that are basically emitted for each of the light source, then we can also get some much better quality of the outputs using the same number of the rays. So those are some of the examples. Any questions on this? Yeah, so here the question might be is that, so we just have seen some very simple example. Like, we are calculating some kind of the, like one step, the reflection with some kind of the Monte Carlo the estimate. But actually what we discussed for the ray tracing is that actually ray tracing is kind of the recursive step. So we are not only caring about some kind of reflection like one single point, but actually we need to basically trace all the trajectory of the rays in terms of like really considering the entire the scene and also the multiple the light sources. So here the question is that how we exactly trace all these kind of rays and in terms of like accumulating all this kind of the information, the reflections. So this becomes like much more the complicated the computation, which also involves either some kind of some tracing, some kind of procedure, which is called the path tracing, or we can consider doing some kind of the global optimization to calculate all these kind of some interactions across the objects and the light source. So these are all about that we're going to discuss in the global illumination. Yeah, so we just have seen some kind of a simple case of the direct illumination. And then next week, we're going to start to discuss some kind of the ideas about the global illumination, really tracing all these kind of like the ray traversal synthesis. Yeah, so this is the end of today's lecture. Any questions on this? Okay, so we basically discussed some kind of the basic concepts of the Monte Carlo estimates. So I recommend you to basically review those ideas and see how those can be basically applied into our some illumination computation. And then we're gonna start to discuss the global illumination from next week. So I will see you next Monday. Okay, thank you. Bye.